Good afternoon, students. Today we are going to start with the next unit that is bioinstrumentation. Okay, and the first is spectroscopy or spectrophotometry. Now, the first thing we need to know before studying a spectrophotometer or how it works, we should know what are the laws on which the instrument operates. Okay, so let us study laws of absorption, right? Now the laws of absorption there are two laws of absorption. Okay, the absorption of light by any substance, by any absorbing material, is governed by two laws. Okay, whenever some amount of light is incident on any substance, any absorbing material, the amount of light a material absorbs depends upon two laws. Number one, Lambert-Bauger law or Bauger-Lambert law, and number two, Beer's law. Okay. Now, the first law, what the first law says, Bauger-Lambert law. The law states that amount of light absorbed by a substance, of course, the amount of light absorbed is proportional to the thickness of the absorbing material, and it is independent of the intensity of the incident light. Okay, what Lambert law says, amount of light absorbed is directly proportional to the thickness of the absorbing material, and it is independent of the intensity of incident light. That means amount of light depends upon thickness of the absorbing material. Now, what is the thickness of the absorbing material? Suppose the material whose absorbance you are measuring. Like last year you have studied estimation of DNA, estimation of RNA, protein. Okay. Now what is the thickness of the absorbing material? See, if the absorbing material is a liquid medium, most of the time it's a liquid, it's a solution. What do? You take the solution in a test tube, right? Rather, when you are measuring the absorbance, you take it in a sample holder, which we call as cuvette. So, what is the thickness of the absorbing material now? The thickness of the absorbing material is now the diameter or thickness of the cuvette. Okay. So, that thickness of the absorbing material is nothing but the diameter of the cuvette. It is also called as path length. It is also called as path length because it is that path of the solution through which the light will pass and the solution will absorb the light. So, thickness of the absorbing material is nothing but the diameter of the cuvette in which the sample is placed or the solution is placed. It is also called as path length. Okay. Now, so what Lambert-Bauger law says, amount of light absorbed is directly proportional to the thickness of the absorbing material. Okay. So look at this diagram. Now suppose 100% light is incident on a sample tube having thickness B, or the thickness of the absorbing material is B. And if it absorbs 50% light, what will happen? If 100% light is incident on it, it absorbs 50% light and 50% is transmitted. If this 50% is incident on another sample, it will again absorb only 50%. Okay, if it is incident on the third, like you can see, the third tube containing the sample, it will absorb 50% of 25, that is 12.5. It will absorb and 12.5 it will emit out. That means absorbance of light in this case is an exponential phenomena, right? Independent of how much light is incident on it, it will absorb a definite amount of light. But that depends upon what? The thickness of the solution, the path length. Like we have represented the thickness here as B. Okay, B, small b is representing the thickness of the absorbing material, the diameter of the tube or path length. So, independent of how much amount of light is incident, it will absorb half of it as shown in this diagram. Okay, so it depends upon thickness of the absorbing material. See, in the first tube you can see when 100% light is emitted, okay, when 100% light is emitted, 50% is transmitted. Okay, why? Because 50% is absorbed. Okay, so some light is absorbed, say for example 50% light is absorbed and 50% is emitted. Now when the 50% light falls on the second tube, it will absorb 50%. That means 50% of 50 is 25 and remaining 50% is transmitted. Okay, so if you plot a graph of amount percentage of light transmitted versus path length, what it will tell you? As the path length goes on increasing, transmitted light goes on decreasing, right? You can see from this graph that as the path length goes on increasing, path length is again thickness of the absorbing material. So if path length goes on increasing, the percentage of light transmitted goes on decreasing. Transmitted means what? Opposite to absorbed. So if the thickness is more, amount of light absorbed will be more and transmitted will be less. Absorption and transmittance are two opposite phenomena. Okay, whatever light is absorbed and the remaining, say if we focus 100% and if I say 75% is absorbed, what will be transmitted? 25%. So the two are opposite terms, transmittance and absorbance, right? So if the path length goes on increasing, thickness of the absorbing material goes on increasing, light transmitted goes on decreasing and light absorbed goes on increasing. That is what Bauger law says. Okay, let us again study what is Lambert-Bauger law. Right. Two fundamental laws are applied that govern the absorption of light by any absorbing material. And the first law was given by French scientist Pierre Bauger, which is also known as Bauger-Lambert law. The law states that amount of light absorbed is proportional to the thickness of the absorbing material and it is independent of the incident light. The intensity, as I have shown in the diagram, the intensity of light that is incident and transmitted is an exponential function. It is an exponential function and we can represent it as follows. Now this is expression for Lambert-Bauger law that is asked in exam and you to study it very carefully. Okay, so how you are going to express the exponential phenomena? I upon I0. How you are going to represent? I upon I0. Okay, right? So I upon I0 is equal to e raised to minus kb. E because it is an exponential phenomena, right? I upon I0 is equal to e raised to minus kb. I0 is the intensity of incident light. I is the intensity of transmitted light. B is the path length, or as I told you, thickness of absorbing material. K is the linearity coefficient of the absorbing material. It is a linearity constant or linearity coefficient of absorbing material. Now you have to remove the power term e raised to minus kb. Now remove it. So what you have to do? Log of it. So ln, okay, ln I upon I0. If you remove the log term, ln I upon I0 is equal to minus kb. Okay. Now this I have taken log of I upon I0 is equal to minus kb. It's not printing here. Okay. Or ln I0 upon I, just reverse it. I0 upon I is equal to kb. Okay. So what is the expression? Ln, that means log I0 upon I is equal to kb. Change the base of the log. So it will become 2.303 log to the base 10. I0 upon I is equal to minus kb. So what is the expression? If you change 2.303 log to the base 10, I0 upon I is equal to kb. Okay. Now, if you study it in depth, what will happen? As I told you, the two phenomena of transmittance and absorbance are opposite. So, as the path length goes on increasing, see the first graph. As the path length goes on increasing, transmitted light goes on decreasing. But as the path length goes on increasing, amount of light absorbed goes on increasing. Okay. So, these two are opposite phenomena. Now, the second law. So, the first law, amount of light absorbed is directly proportional to thickness of the absorbing material and it is independent of incident light. Because it is an exponential phenomena, you represent it as, okay, I0 upon I is equal to e raised to minus kb. Remove the power term and you get I0 upon I is equal to kb. So, second law of Beer's absorption is Beer's law. The law states that amount of light absorbed by a material is proportional to the concentration of the absorbing material, absorbing substance, absorbing solution. Okay, what Beer's law says? It is Lambert's-Beer's law, or simply we call it Beer's law. What is Beer's law? The law states that amount of light absorbed is by a material is directly proportional to the concentration of the absorbing substance or absorbing material. Now, how are you going to represent this expression? This is mathematically expressed in the form of the same above reaction as we discussed in the for Bowger-Lambert law. Okay, so it will be 2.303 log to the base 10 I0 upon I is equal to K dash C. Again here K is the absorptivity constant, right, and C is the concentration. What we wrote there, 2.303 log to the base 10 I0 upon I is equal to B. That means path length, right, because it is directly proportional to path length. Here it is directly proportional to concentration, right. So there we wrote Kc and here is Kb and here we wrote K dash C. So mathematical expression for Beer's law is 2.303 log to the base 10 Li0 upon I is equal to K dash C. C is the concentration of the absorbing material and K dash is the absorptivity constant. K and K dash are both same. That means absorptivity constant. Now when you combine the two law, Lambert-Beer law. Okay, now this is, we are going to combine the Bowger-Lambert law and Beer's law. So it is called as Beer-Lambert law or simply Beer's law. You combine the two laws, you can express it as log of I0 upon I is equal to KB and KC. Combine it. So K and K dash both are constant, absorptivity constant. We combine the two constant and write only one constant, that is A. Okay. So A, B, C. So log of I0 upon I is equal to A, B, C. This is the expression for Lambert's-Beer's law or simply Beer's law. What is I0? We know amount of light, intensity of incident light. I, intensity of transmitted light. C, concentration of absorbing material. B, thickness of absorbing material or path length. And K and K dash are absorptivity constant. They becomes a single constant A. So A is absorptivity constant. Now this is dependent upon the absorbing substance, the wavelength of light used and the unit used to specify C and D. Okay. So when the amount of light absorbed will depend upon wavelength of light exposed and all. Right. So if I need to write the expression, how will I write? I upon I0 is equal to e raised to minus kb. Now I remove the term e. So you remove it. So it becomes minus kb. Right. And in that case you have to apply for log. Now when you change the base, you remove this minus sign and it becomes, if you remove the minus sign and make it log, it becomes ln I0 upon I is equal to kb. Now we change this ln to log to the base 10. So you have to put 2.303 log to the base 10 I0 upon I is equal to kb. That is the expression for Lambert's law. Expression for Beer's law, instead of B we take C. You combine the two laws and it becomes log of I0 upon I is equal to ABC. Okay. Now, so this is Beer's-Lambert's law or Beer's law simply is a linear relationship between absorbance and concentration of absorbing species. The general Beer's-Lambert's law is A is equal to ABC. Now what is A? Where A is measured absorbance, Small a is wavelength dependent absorptivity coefficient or absorptivity constant. B, path length. C, analyte concentration. Now what is A? A is log of I0 upon I. Okay. So A will be calculated as log of I0 upon I. That means log of I0 minus log I. But I0, that is amount of light incident, is, or intensity of incident light is always 100%. So I0 is 100%. So log 100 is 2. So A will be equal to 2 minus log I. That means amount of light absorbed. If you want to calculate absorption, it can be calculated as 2 minus log I. Or there is actually a simpler method of calculating the absorbance. Okay. So optical density, absorbance is also called as optical density. Okay. Optical density is directly proportional. This is the statement for Beer's law in the other way. Amount of light absorbed or optical density is directly proportional to the concentration of the absorbing material if path length is constant. Every time we do not change the sample holding device, we do not change the cuvette. So the thickness of the cuvette remains the same. So path length is always constant. Whenever you are doing some kind of measurements of absorbance, the path length is always constant because the cuvette diameter is always same. You use the same cuvette. So amount of light absorbed or optical density is directly proportional to the concentration of the absorbing material if path length is constant. So we can calculate the optical density from the concentration. Okay, sorry. If we know the optical density of any substance, we can calculate the concentration of the. If we know the optical density, concentration can be calculated by using the following formula. What is the formula? Concentration of unknown sample is equal to optical density of unknown into concentration of standard divided by optical density of standard. You have to use a standard sample solution there. The standard solution is the solution whose concentration is known. Okay, so the concentration of unknown sample is equal to optical density or absorbance of unknown multiplied by concentration of standard divided by absorbance of standard. This is about Beer's law and how to calculate the amount of light absorbed. Now, when you study Beer's law, there are certain limitations of Beer's law. Okay, where the law fails or the linearity of the law, the collinear, there is a linear relationship, as I told you. Linear relationship between what? Amount of light absorbed and concentration. That means as the concentration of the solution goes on increasing, amount of light also goes on increasing. Right. So there is a collinearity or linear relationship between concentration and absorbance. Yeah, concentration and absorptivity or optical density. Meaning what? Amount of light absorbance or optical density goes on increasing when concentration goes on increasing. Right. So linear relationship. But this linear relationship fails. Why? There are certain reasons for where Beer's law fails. That is limitations of Beer's law. So we are going to study the limitations of the Beer's law. The linearity of the Beer's law, Beer-Lambert law rather, the linearity of the Beer-Lambert law is limited by chemical and instrumental factors. Okay. What are the causes of non-linearity? Right. What is the Beer's-Lambert's law? If you plot a graph of absorbance or optical density versus concentration of the solution, as the concentration goes on increasing, the absorbance also goes on increasing. You will get a straight line graph. Okay, meaning what? With the increase in concentration, amount of light absorbed also goes on increasing. Right. Now, but deviations do occur. So we have to study the deviations from the Beer's law. They may be because of chemical factor or by instrumental factor. So the first factor which is responsible for deviation of Beer's law or limitation is concentration. Right. If the solution is highly concentrated, right, the deviation in absorptivity coefficients are observed at high concentration, more than 0.01 molar. Why? Due to electrostatic attractions between the molecules which are present in the close proximity. Okay, when solution is highly concentrated, molecules are present in close proximity and there is electrostatic interaction. Molecules may fuse, two molecules may combine and form a dimer. Not just that, they also form aggregates. Okay, if the solution is concentrated, molecules to only two molecules do not combine to form a dimer. Many molecules combine to form an aggregate. So the aggregated form of the sample brings about scattering of light. Okay, scattering of light by these particles or aggregates or dimers occurs, and when scattering of light occurs, you get a faulty result. The amount of light absorbed may be too high, because scattered light is also measured and transmitted light is also measured, right? So you get a higher value. Then changes in the refractive index. When the concentration of the sample is more high, then there is change in the refractive index. There is change in the chemical equilibria as a function of concentration. So because of formation of aggregate, because of formation of dimerization, all these because of electrostatic attraction, the the light is scattered by the aggregates, and along with the absorbed light, scattered light is also measured, and we get faulty results. Or here the concentration or linear relationship between concentration and absorbance fails. Okay, so the concentration should not be too high. Now what happens in case of proteins if the concentration is too low? Okay, in case of proteins, it is not that the high concentration is responsible for deviation in Beer's law. The low concentration is also responsible. So in case of proteins, if the concentration is too low, then also we get faulty results. Okay, the second factor responsible for deviation is temperature. There are certain chemical reactions, biochemical reactions, which are temperature dependent. Okay, and at a particular temperature, the amount of light absorbed by the sample will be definite. But if the temperature changes, with the change in temperature, the absorption by the substance also goes on changing. Okay, so if a reaction is temperature dependent, immediately as soon as the reaction is over, you have to measure the absorbance, because if the with the fluctuation in temperature, the amount of light will also, the amount of light absorbed will also go on changing, and you will not get a linear relationship graph. So in case of temperature dependent reactions, you have to be very careful, because change in temperature will lead to faulty results. Next one, the third factor is sample instability. Most of the samples are colored. When you perform the reaction, when you go on adding the you can say chemicals, a color reaction develops and you get a colored product. And most of the time, or in some cases, the colored product formed is unstable. The color intensity formed is unstable, right? So in such colored derivatives or in colored samples, when the color is unstable, as soon as your reaction is over or reaction time is over, immediately measure the absorbance. If you prolong the absorbance time, the result will be faulty. You can say you will get different results, because the color intensity may change, right? So when the sample is unstable, when the color formed by the sample after reaction is unstable, measure the absorbance at the earliest or as soon as the reaction is over. If you keep the solution, the intensity of the color will change and your results will also change. Next factor is fluorescence. If the sample is fluorescent, then your instrument or your detector will detect both light absorbed as well as fluorescent light emitted by the substance. So if your substance is fluorescent, then along with normal light that is absorbed, fluorescent light will also be measured and you will get wrong results. Okay, your results will be different. So fluorescence is also responsible for faulty results, deviation. Turbidity. If the sample is turbid, the amount of light absorbed will be more. So absorption or optical density is always higher in turbid samples. So you have to take care that your sample should be clear. Okay, next, instrumental limitations. There are certain limitations, there are certain deviation, okay, that may also occur because of, from Beer's law, because of limitations of the instrument. right? So the first is imperfect monochromacy. If the instrument is not giving perfect correct monochromatic light, then it will give faulty results. Deviation from Beer's law will occur. So imperfect monochromacy, that means monochromatic light emitted by the instrument is not proper, or there are too many light rays which are coming in. Stray radiations reaching the detector, radiations from here and there in the environment, which we call as stray radiation, radiation not coming out of the sample, the stray radiation, unwanted radiation in the surrounding may also reach the detector, and they will also be counted. So there will be deviation from Beer's law. Linear relationship will not be followed. So instrument limitations, under instrument limitation there may be not a perfect monochromatic light, imperfect monochromatic light, stray radiation may also be counted, and sensitivity changes in the detector, power fluctuation of the radiation source. If there is power fluctuation and in the radiation source as well as in the detector, then also you will get wrong results or haphazard results. So instrumental limitations may also lead to deviation from Beer's law, right? So we have studied Beer's law, and what are the factors that are responsible for deviation? That is concentration, temperature, sample instability, then turbidity, fluorescence, and instrumental limitation. So that is all for today. Rest we'll study next time.